Okay, so this is lecture 1. We're going to do sections 1 through 3 of sections 1 through 3 of chapter 23. So this we're talking about electromagnetic induction. And so we're going to induce an EMF in a wire by moving it through a magnetic field. Okay, so there's a couple of ways to do it. We can either move the magnetic field or we can move the wire. All right, so we're going to talk about all those things. So we talked about electric motors in class, and they have loops of wires going through them, and they are in a magnetic field because there's little magnets in them. And this is the same thing, only we're going to look at it from a little different perspective, okay? And we're going to add a little bit to this. Okay, so let's say we have a magnet, and it's going to go through a loop, all right? And Lab 8 has this, has this very thing. It has a magnet, and we let it go through a loop, and we measure the voltage that is generated. Okay, so we're measuring the EMF. So this is exactly the experiment we do in Lab 8. Now, here we have a loop. I'm going to just say that it's a perfectly round loop. Okay, everybody wants perfection. So we're going to just say that it's a nice round loop, all right, with a radius r. Now, the magnet is going to go through the loop, okay? So we can think of this two different ways. We can think of the magnet moving in and out of the loop, or we can think of the magnet staying still and the loop moving, okay? Either way is fine. What's going to happen is we're going to generate a current in this loop, and we have this current meter set up over here to monitor which direction the current is going. If it goes in this direction, it's positive. If it goes in this direction, it's negative. And, that's it. We're going to measure. Okay, so it turns out that if we put the magnet in north into the loop, north end in first, and it's moving through, then the current is going to move in the negative direction, so that it's going to move in this direction. Now, the same thing would happen if we move the loop over the magnet, right? Because the magnet or the loop, they have no idea what's happening. They're just noticing this change in magnetic field, and so then they're developing this current as a result. Okay, so if the magnet goes this direction, or the loop goes this direction on the magnet, if it's in this configuration, north to the right and south to the left, then the current is going to be generated like this. We can flip the magnet around and do the same thing, but what's that going to do for us? We're going to have it go in this direction. It's just going to flip the current around. Okay, so it used to be going to the right, now it's going to go to the left, and vice versa. And the same thing happens with all the different ways that we can move either the loop or the magnet. Okay, so it looks like there's 8 different things that can happen here. Okay, so there's 8 choices of ways to induce this current. And so we are going to look at things a little bit differently than we have been, and we're going to introduce this thing called the magnetic flux. So the magnetic flux, it's this symbol phi. Okay, once the page is filled, my writing doesn't work so well. So phi is the symbol, and it's a magnetic flux. It's basically the dot product between B and A, and we'll talk about what A is in a second. B times A times the cosine of theta. If you know the magnitude of B and the magnitude of the area, Then you multiply that by the cosine of the angle between them, and you'll get your answer. Okay, so here's our loop. We've got a loop inside of a magnetic field. The magnetic field is pointing into the page. So we have an area, it's our width times our length. Easy, because that's why we like rectangles. And then B is the magnetic field, so that's where we're at. Now, what is the vector A? So we were talking, you can get that, we need the vector, right? We need to know the angle between B and A, right? Because here's what could happen. We could have a B going in this direction, and then A could be going in this direction, and so then our angle between them would be theta. Okay, fine, but it's an area. It's not a direction. So what is A? Well, remember when we found the normal force on a plane? Well, we're going to be doing the same thing. It's the normal vector, okay? So A is just like the normal force vector, and it points in the same direction. In our case, it could either be pointing into or out of the page. A could be here, and it's either pointing into the page or it's pointing out of the page. I'm sorry, I just got them backwards. Out of the page or into the page. And we are the ones who define which thing is positive and which thing is negative. Okay, so that's up to us. All right, so we say, oh, well, we want it to be this or we want it to be that, but it's always normal to the actual area. Okay, so the area in our case is parallel or anti-parallel to our in our picture. Okay, so but they might not always be, right? What if the angle is what if our area is pointing in this direction, okay, and our B field's pointing in this direction? Then theta is the angle between A and B, and we want the component of A pointing in the B direction or the component of B pointing in the A direction. So it doesn't matter either way. So here's how we've got it. We could either have B times A cosine theta, which is the component of A going in the B direction, or we can have B cosine theta times A, which is the B component in the A direction. All right, so whichever floats your boat. You do it however you want, but get that angle between them and multiply it, find the cosine of it and multiply it in there. Okay, you'll get the proper flux when you do that. So now that we know what the magnetic flux is, we can move on, and we're going to look now and see Faraday's law of induction. So what did Faraday do? He made a wire loop, all right? And he gave it an area. Our wire, I don't know what kind of wire loop he used. Ours is going to be an area of a circle, all right? Our wire loop is a circle. And then he placed a B field through that loop, okay? So he just started running, some B field through the loop, and something like this, and that's a B for B field. Okay, so fine. When he noticed that when phi changed, so we have some area on the inside of this thing, and either the B the B field was increased or decreased or whatever, he noticed that an EMF was generated and he got current through his ammeter. So somehow either the current went up or down. He didn't, we don't know what happened. We could go back and read his papers, but the current either went up or down, and it was measurable. And so he found that this and this were very important. So he figured out that delta phi was the thing. Phi is our magnetic flux. Okay, this is the symbol phi. So phi is our magnetic flux, and the EMF was proportional to delta phi. So that was the first thing that he noticed. The second thing that he noticed was that the EMF was inversely proportional to the time. So if the time went up, the EMF went down, and if the time went down, the EMF went up. So that's kind of interesting. And then lastly, he could add more loops. So he could have more than just one loop. And the more loops he added, the higher the EMF went. So you add a lot of loops, you get a lot of EMF. So he noticed that too. So then he combined all these three observations and he got this equation. Okay, so he got the EMF is equal to the number of loops times delta phi over delta t. That's Faraday's law of induction. Okay, so Faraday's law of induction. Now, this minus sign is extremely important. It's so important. No, most of the time we don't care what the minus sign says. And we'll talk more about how we can ignore it later. But it means that the EMF makes a current. Okay, so this new EMF is going to make a current. And that current is going to move in a way that the generated new B gen, we're calling it B gen, or we could call it B induced, whatever it is, but this new B field that the current is generating opposes. It's going to oppose the change in flux. Okay, so if the flux is getting bigger, then the B field will be one that reduces that flux. If the flux is getting smaller, then the B field will be such that it makes it bigger, okay? And that negative sign that we have there is Lenz's law, okay? And that shows itself in Faraday's law. So, Faraday's induction law. Now, so follow this story for a second. Here we have this magnet, right? We're gonna send it through this loop, and as the magnet approaches the loop, you can tell that the B field is gonna really increase. So our B field right here, once this part starts going through here, our B field will kind of be like at a maximum, right? As it's going through right in here, that's the max B field. So it's going to go up as it gets closer, all right? The current generated by our new EMF is going to be generating some current, and the current, we don't know yet which direction it's going to go. We don't know if it's going to go in this direction or this direction, but there's definitely going to be some current there, and it's going to be fighting that. And it's fighting the change. This current is fighting the change. So what is going to fight that growth of flux? Well, the new has to go in the opposite direction. This is the new magnetic field going in the opposite direction. Okay, so in order to generate that new field, our current has to look like this. it has to go that direction to generate this new fighting current, fighting B field. Sorry. Okay, so the new B field is produced, and it has to be like that, and then therefore we use the right-hand rule to figure out which way that current had to go to generate that B field. So we have two B fields, all right? Two. One is the new, and one is from the bar magnet. Okay, so the bar magnet, the bar magnet is one, that's our initial B field going through the wire, through our loop. Then the induced current creates another B induced that opposes it. So there's two B fields, okay, two. One is adding, one is subtracting from the other, okay, kind of balancing it out. They're trying to, the induced is trying to oppose it and balance the whole thing out, okay? It is opposing the original change in flux. So what if we're leaving? So now our magnetic field is leaving, our bar magnet is leaving, and that means that phi is getting lower, so it's negative because I initially was more than I finally. So that gives us this negative sign. So now that it's negative, the EMF will be made to cause a current that goes in, opposes this decline. So that means that it wants to increase our magnetic field. So what does that look like? That's going to be adding a magnetic field like this. How do we add a magnetic field like that? What's our current have to look like? Well, in order to do that, my current has to go in this direction. Okay? So that adds a current, and we are generating an EMF that causes this current to go in that direction. Okay, so I already kind of did what is the direction of the current. Of course, there's our new induced magnetic field, and it has to oppose it. So in order to create that new induced magnetic field, we're creating this. We have to have a current that flows in that direction to induce this magnetic field. So what's the order of things that happens? The change in flux happens first. Then we get an EMF because of the change in flux, but the EMF is driving the current that opposes the change in flux through its own induced B field. Okay, so that's how it goes down. As far as you know. No, I'm just kidding. As far as I know. All right, so we're going to see this again. Like I said, Lab 8 does this exact thing, and we drop a magnet through a solenoid, and it's made of many loops. Our solenoid's made of many loops, so we're going to get an EMF that looks something like this. Now, let's go back to Faraday's law. Our EMF is going to be minus the number of loops. So I think for that lab, the number of loops is 3,300. Okay, and then we're going to multiply by the delta change over the delta time, and all of those things in the lab are measured. So we can come over here and we can go, oh, well, how much time does it take to get from here to here? We can get that delta time. And then what is our volts at this point? We can figure that out. And now we know our voltage. We know what our delta time is. We know what our N is. And we can figure out our change in flux from there. So it's kind of pretty cool, actually. it's a nice thing. And in fact, we're not doing it. I selected way too much. We really are going to be going from here, right? Because we want the max EMF. So our delta T is really going to be this bit here. And we still know our N, and we'll have the magnetic flux. And we can say, oh, well, then that means we can measure the B of the, we can measure the B of the magnet, because B of the magnet, can we do that? No, we need to know the area. We can estimate the area. Yes, the area is approximately what? Pi r squared, and r is probably, I don't know. R is probably equal to 0.077 centimeters? No. 7 millimeters. R is probably equal to 0.007 meters. Probably about that. And if we know that area, we can figure out the flux. Then we can say, oh, well, our delta flux is equal to B times the area. And we know what the area is, pi r squared. And so we can figure out what the magnetic field is. And you guys can do that when the time comes, if it ever does for you. Time comes for us all. So good luck. All right. Using Lenz's law. This is how to do it. Like, if you're going to do a problem, make a good drawing, okay? And it takes practice. It's hard to do good drawings, and Lord knows I try, and I'm sorry I'm sorry for my drawings. Determine if the phi is growing or declining, okay? Is it getting bigger or getting smaller? The new induced magnetic field opposes that getting bigger or getting smaller. So draw the direction accordingly, okay? So draw that direction. Then use the right-hand rule to know which way the current is flowing that has to generate this new induced magnetic field. And once you have that, then you know which direction your EMF is going, and you know that it's being induced by Faraday's law of induction. With, don't forget, the very important Lenz's law, right? This Lenz's law, very important. All right, let's do an example. So this is straight out of the book. We've got a loop. The radius of the loop is r is equal to 0.06 meters. We've only got one loop, so that's easy. And we can take that radius and figure out our area, so that's nice. In fact, this could be the area roughly of our solenoid that the magnet drops through. That's a good approximation of the area right there. So B is going to increase because it's heading into the loop. It's going to increase from this to this, okay? And it does so in this amount of time. So nice. So what is the magnitude of the EMF? Well, the angle that this is all happening at is 0 degrees. So the cosine of 0 is 1. So we can just get rid of, every time we see cosine of 0, we can say that's 1. And so we've got our phi initial is B initial times A. Our B final is B final times A. That's our phi final. And then this minus this is our delta magnetic flux. And we can factor that out, so that's kind of neat. And now we can plug it all into this. Now I'm making it a magnitude, okay? Because we really just want to know what the magnitude is. We don't know which direction is which and all the ways that the different currents could go and all that stuff. They don't give all that to us. So we just want the magnitude. So we're going to do that. So here's our thing. We're going to say, okay, n equals 1. We've got our area here. We've got our B final. We've got our B initial. And then we've got time. And we just plug those things in to our little calculator. And we end up with 22.6 millivolts. Okay? So we don't need the direction. And we can figure it out if we drew a nice diagram, but nobody's asking for it, so nobody cares, so we don't need to do that. So now, there's another way to get phi to change. So I'm gonna skip a little bit here, and we'll come back. Phi can change in 3 different ways. First of all, we can have change in the magnetic field, which we just did. Okay, so this B could have a final and an initial, and that'll give us a delta phi. However, we could also have the area final be different than the area initially. Okay, and then the B stays constant, and the cosine of theta stays constant, so this guy is what changes. Okay, that gives us a delta phi. Or maybe the angle is changing, the area stays constant, the magnetic field stays constant, but the angle, it's rotating by some angle through here. Well, that could happen too. Both of these are both called motional EMFs, not emotional EMFs, motional EMFs. Okay? So, now, we all know that life is complicated and all 3 of those things could change, right? But we're not going to do any problems that do that, all right? We're going to do problems where either the angle is changing because of a rotation through this thing, right? So our circle is rotating like this, and the angle just keeps growing in that way. Okay, so that could happen. Or we could have something like this, where we've got a bar that moves, and in our case, the velocity of the bar is moving the bar from a smaller area to a larger area, and it's starting at x naught, and it's moving its way to x final at some constant velocity. So that could be happening too. Now, our direction of area and of the magnetic field that we have this thing immersed in, those 2 things, the normal of that area, we can either say it points into the page and then it's parallel like this, or we could say that it's pointing towards us. It all depends on how we want to do it. In that case, it's anti-parallel, and either way, our theta is going to give us either a -1 or a 1, so why make things complicated on ourselves? Let's just keep it at 1, and we'll use this one where our normal for the area is pointing into the page. Okay, so let's do that. All right, great. Now let's talk about this for a second. So our bar is moving, and the bar is conductive. Okay, so this bar basically is a wire. Come on now. Is a wire, right? This bar, and it's like steel or something, and it's allowing current to flow. All right, and it's going from here to here. Here's the current wire going that way, and it's just sliding on these rails. Okay, so let's start with our constant velocity. Our constant velocity right here is delta x over delta t. All right? Okay, that's fine. We know also that the area is whatever this x is times L, right? Here's our length L, and here's our distance x. So area is increasing as x increases. That means that delta area is equal to L delta x. And x final minus x initial is what delta x is. And so we're going to figure out what V is, or input V, which gives us delta x, x final minus x initial, or delta x, equals V delta t. Okay? All right. So now we're going to substitute V delta t in for this delta x, and that's going to give us this. So nice, and that's our delta A. So now we can take that delta A and we can substitute it in here, which means now we're left with B times LV delta T. Our N is equal to 1. We've only got one loop, right? There's only one loop going around in this circle. Okay, so that's our one loop. So now we're gonna input all these things into our EMF. So we're going to input those things, and we're going to come up with BLV delta T, but then we're dividing by delta T, so the delta T's cancel out, and that leaves us with an EMF of BLV. Now this is important. It happens to be that first of all, our area normal is parallel to B. It also turns out that the velocity is perpendicular to both A and B, okay? But more importantly, it's perpendicular to B. If it wasn't, then we'd have to find the angle between them, okay? And we don't want that. So that's important, that all of our stuff gives either the sine of 1 or the cosine of 1, right? This is important, and then the sine of 1 is important. So if we were to have more loops, which we could, then we would have this in general, okay? So in general, we've got our EMF equals NBLV. And again, my suggestion is that you figure out what your EMF is. Pardon me. We figure out what this EMF is first, the magnitude of it. Then use your right-hand rule to get the direction of the generated or induced current. All right, so let's do an example. This example's motional EMF, figure 23.12 in the book. It's also a problem in the homework, so you're going to enjoy this one, I hope. We've got some length between a spaceship and a satellite, and they're hooked together by wires, okay? One is a wire, and one is the discharge going back. It doesn't matter. Think of them as wires, current flowing one direction and the other. The area of this thing, let's see here. The area of this thing is going to stay constant. So, and we don't really care what that is. We're moving, the L is this. That's the length from one side to the other. We're moving with this velocity. We know that this is the magnetic field of the Earth, and we're moving through that, all right? So what is the EMF generated? Well, it's simple. We're just going to plug in those numbers. And so I've got my 5. I'm going to multiply that by 2. I'm going to multiply that by 7.8. So I get 5 times 2 is 10. So 10 times 7.8 is 78. But I'm going to take this, and this, and I'm going to add them all together. So 4 plus 3 is 7, minus 5 is 2. So I've got my 10 to the 2 there. So all of those things multiply together to give me 7.8 times 10 to the 3 volts, or 7.8 kilovolts. Okay, so this is lecture 1. Thank you for paying attention, and rewind and all that stuff as much as you'd like.